Next is Laplace criterion, which is simple average. So let's populate the costs here for 3 possible states of nature and 3 possible decisions, and it is simply average of each decision. Okay, then it is the minimum of that. We'll use that one. All right, and then minimizing maximum regret. All right, so here again, let's populate the costs. Now, this is a cost problem, so you have to be careful. The best possible outcome for each state of nature is the minimum value. So minimum, that's the best possible value. So now the regret or the opportunity loss will be the financial outcome, the cost of a given decision under a given state of nature minus the best possible. So best possible is going to be the smallest value. Now this needs to be absolute referenced with column floating, row fixed. So I have to do F4 twice. Alright, so now we copy that and copy across. So now we have regrets now. Okay, so at this point we are looking at maximum regret and you want to minimize that. So what is the maximum regret for each decision? Max. All right, and then we want to minimize that. Minimize the maximum regret. Okay, and the decision is that. Okay, now continuing with the cost problem, we want expected monetary value. So we have probabilities now to be assigned for each possible future state of nature. So let's assume equal probability for start to start with. Okay, so let's say 1/3. Don't type in 0.33 like that. So that's very inaccurate. So when it is possible to enter 1/3 like this, you should do it because that's the more accurate way of expressing the probability. Now copy across and see if you sum these, it will be equal to 1. If you did 0.33, it's not going to sum to 1 properly. So expected monetary value now is sum product of the cost with the corresponding probability. The probabilities must be absolute referenced. So now the values will be paired, multiplied, and then added up. So that's what we want for expected monetary value. So copy that. The best EMV is the minimum of those. Okay. Now the decision is machine C. Now the expected value of perfect information. Okay. Sometimes this is also called not EM, so EV with PI, and EV, expected value or expected monetary value. So EM, EV, some people use EV, some people use EM. All right, so that should be EMV. The expected value of perfect information. All right, so now let's populate the costs. Okay. So the best EMV is this, but what would be the EMV with perfect information? Okay, with perfect information, you will, okay, the outcome would be the minimum. So whatever the state of nature may be, under that condition, you would be in the best place. Okay. With perfect information, you would be. So minimum is what that would be. So now if you do a sum product of the best outcome under each state of nature and the probability, of course we have to fill out the probabilities, which I will in just a second. So let me get these probabilities from here. Then what you get is the expected value with perfect information. So the expected value of perfect information would be, okay, since this is a cost problem, you have to go like this. So it can be expected value cannot be, expected value of perfect information cannot be negative. So like that. Now expected opportunity loss. Okay, this is the same opportunity criterion from here, right? So we need the probabilities and then the regrets. The regrets will be the outcome minus the best outcome. So this is a cost problem, so best outcome is going to be smaller than where you are. So that should be absoluted for row and keep column floating. So now copy that across and down and across. Alright, so now we can do a sum product of the opportunity loss with the probabilities, and the probabilities must be absolute referenced. Okay, so now we want minimum expected opportunity loss, so min of that, and then the decision will be